Hello. Today we shall be starting on our next lesson concerning the second part of our course of calculus. The first part was differentiation, which we ended with in our last lecture, and now we start on our second part of the course. Now, integration, as I have told you in our first introductory lecture, it was discovered prior to differentiation. Yet because Newton and Leibniz facilitated the idea, the concept of integration by introducing or by discovering their fundamental theorem, in which you have to use the antiderivative in order to calculate areas, and therefore this knowledge of antiderivative must be based, of course, on our previous knowledge of differentiation. And this is why differentiation is usually taught before integration. Whereas from the historical point of view, it was integration which came first and then differentiation, and in fact, by several centuries. Now, the drawback of the theorem of Newton and Leibniz is that it was considering only continuous functions. And this is why when Cauchy intervened with his fundamental theorem, it was the same one actually, but it was an extension of the other one because it released the condition of continuity, and the function may not be continuous, and yet only if it has an antiderivative that it's an integrable, and you have his fundamental theorem. Now, later on, it was found that the function may not be continuous or having still an antiderivative, and these two conditions may not be there, may not exist, and yet the function is integrable, and this was the role in the 19th century when Riemann came about and introduced his Riemann sum, the limit of which, if it exists, leads to the integral, which we call the definite integral. But then we are back to square one, because actually what he did is that he summed up area, the same idea like it was done in the ancient times by Archimedes. The only thing that Archimedes himself or the mathematicians of the ancient time did not consider the phenomenon of continuity, because all practical applications in which the functions are, in which the ones that we use are always continuous. Now, integration, the idea of integration or the meaning of integration is to accumulate areas together. And usually integration is taught in colleges and universities using two different routes, or in other words, there are two alternatives for teaching integration. Either you start by the rigorous approach, which is usually taught in analysis. By Riemann, you define the integral that is Riemann integral, and then you take a special case when the function is continuous. But then there is another approach which I prefer myself, and this is the one that I'm adopting in my course, usually with my students, is that I introduce first the fundamental theorem, and then I go and proceed for the generalization when I expose Riemann integral. The reason for this approach is that usually students, what they do in their study all the time is that they calculate antiderivative of functions because they wish to apply the fundamental theorem. In other words, it's the fundamental theorem which interests them because it has all the applications, in fact, and very seldom you find cases in which you have to apply the Riemann integral. Now, during the course of time, the meaning of antiderivative, it has been brought about the chronic question whether antiderivatives are integrals or not. And actually this was answered efficiently by Cauchy, because from his fundamental theorem you have the fundamental theorem of Cauchy tells you that the integral from a to x of f of t dt is equal to capital F of x minus capital F of a, where f is having an antiderivative capital F. Now, if you differentiate this with respect to x, what you get here, you get f of x, which means simply that what you have here is an integral, and this integral, when you differentiate it, you get f of x. In other words, this is an antiderivative. And then Cauchy was able to answer this chronic question whether antiderivative are integrals or not. Yes, indeed they are, except that they are indefinite ones. In other words, they don't give a number like the definite integral. On the contrary, they give a function. But you can consider them as integral because here, when you differentiate it, you get the same function you started before. And actually, this was the same approach that was adopted by Newton himself when he took a function f of x, and his method was called the method of inverse tangent in the 17th century, is that he took a function f of x, and then starting from the point A and ending, for example, an x, and he called this area A of x, whereas when he added a small increment of area at the other point x plus h, what you get is A of x plus h. So the difference between the two is equal to the area of this small rectangle here of base h and of height almost f of x. So you get here h f of x. So what you do now, when you divide both by h here, what you get here is that f of x is equal to this quotient. Now this quotient here is the same one we use to calculate the derivative of a, except that the limit at the time of Newton it was from the concept point of view, it was known, but not from the mechanical point of view. In other words, it was because it was introduced later on, almost a century later on, by a Czech priest called Bolzano and from Cauchy himself. And from there on, they studied continuity and differentiability, etc. So this quotient here we find, which is a of x plus h minus a of x divided by h. When you take the limit, when h approaches 0, what you get is dA by dx. So actually, what Newton really has proved is that the derivative here of the area is the function. So this area here is no more than antiderivative of small f. So at the same time, A is an antiderivative, and A represents the area, so that we can say now that antiderivatives are integrals, but they are indefinite integrals. Why? Because these antiderivatives or these integrals yield functions of x, and they don't give a number like the definite integral. Now, in this lecture, we shall be speaking about antiderivatives in general, and we shall start by, first of all, defining the notion of the indefinite integral. Then we should state some remarks about them, then their properties, and finally we give a simple form of differential equations and to tell you how we solve them. Now, to start with the notion of the indefinite integral. Well, the indefinite integral, which I said before, it's the antiderivative of the function f. The idea is that you have a small function, small f, and you wish to calculate another function, capital F, of which the derivative of which is equal to small f. And that's the idea. Given small f, find capital F such that f dash is equal to small f. So what you do is that, for example, you take a few examples. Here you have, for example, small f maps x into x cubed, which is the antiderivative of this function f. The antiderivative is 1 over 4x to the power 4. How did you know that? Very simply, all you have to do is that you differentiate 1 over 4x4, you get x cubed, and therefore 1 over 4x4, x to the power 4 is the antiderivative of x cubed. Again, for example, you have 1 over x. What is the antiderivative of this function here? It's the logarithm of x. Why? Because when you differentiate it, you get 1 over x. As in fact, in this situation here, when you have, for example, 1 over x here, the integral of 1 over x, you can very well write it logarithm of x. There is no point of writing ln mod x, but you may wish to use the other form and write ln modulus x. The reason because why are we using antiderivative? It's not an intellectual exercise. No, you wish to calculate antiderivative because you are bound, or you wish to later on to apply them in the fundamental theorem. It's not an exercise, as I tell, intellectual exercise. No, you bound to implement the later on the fundamental theorem. And when you have, for example, in this situation, 1 over x is a curve like this, which has a vertical asymptote at x equal to 0. And suppose, for example, you wish to calculate the area beneath the graph from the point, for example, minus 3 to minus 2. What you do is that you integrate 1 over x, for example, from minus 3 to minus 2. So you obtain ln x, and then here you substitute here minus 2 minus ln minus 3, which you get nothing. Why? Because the curve of the ln is only has a domain x greater than 0. So there is no such logarithm of a negative number. So therefore, you cannot use this formula, and you have to use the other formula by putting ln mod x. In which case ln mod minus 2, which is ln 2, you get ln 2 minus ln 3, and this is actually a negative, has a negative sign because the area is beneath, or the region is beneath the x-axis. But the question is, does ln mod x had the same derivative as 1 over x? Yes, indeed it has, because if you wish to calculate the derivative, what you do here, you use the chain rule we just taught you a little while ago, and here you use the chain rule. You can check this and put it equal to u, so you get the derivative with respect to u, which is 1 over u, which is mod x again, time the derivative of mod x, and this we saw in our differentiation lesson, divided by x, so they cancel out together to obtain 1 over x. So in fact, ln mod x and ln x have the same derivative, except that ln x is defined for x greater than 0, and ln mod x is a curve which is defined for all values of x except x equal to 0. So it depends really on the application. But for my students, when I tell them obtain the antiderivative of the function f given by f of x 1 over x, you can rightly say it's ln x. Now, some remarks about antiderivatives. Now here, first of all, the idea is not that simple, as we said. Of course, you have to fetch for a function the derivative of which gives the original function, but it's not easy all the time because there are functions which do not have antiderivatives. For example, this function here doesn't have an antiderivative. According to a theorem we should not dwell into here, but anyway, this function has no antiderivative. It's a function, it's a sine function. It's equal to 1 for x greater than 0, and minus 1 and 0 when x equal to 0. This function has no antiderivative because it does not satisfy a certain criteria. Again, not every elementary function has an antiderivative in the form of elementary function. For example, some teachers say, for example, that cosine x squared is not integrable. You cannot find an antiderivative for this function. Indeed, you can, because according to the first fundamental theorem, this function x squared is continuous, and you have here a composite function of a continuous function, and therefore is continuous. And the first fundamental theorem asserts that if you have a continuous function, therefore it has an antiderivative. But the problem for these kind of functions like cosine x squared or e to the power x squared, these functions, you cannot represent the antiderivative in the form of elementary function, and this is why the student cannot proceed further to calculate antiderivative of these sort of functions. So here again, there is another difficulty associated with antiderivatives. Now, as I said here, this function is continuous, but there is no elementary function, capital F, which represents such an antiderivative. Again, finding the antiderivative of function is not that easy. Why? Because this is an inverse operation. And you find this all the time in operation, where you have, for example, division is much easier than multiplication. Even when you start driving, the first gear is simple, then you return with your car to park, for example. Going forward, addition is easier than subtraction, etc. So you find that finding the antiderivative is much more tedious than finding derivatives of functions. Again, these functions, for example, all of them have an antiderivative, but in the form of elementary functions. But it's not easy to find them. You have to do tedious or difficult operations in order to arrive at the antiderivative of these functions. Again, there are no, for example, integration. There are books specialized in integration. You find big books like this, and it contains all form of indefinite integrals. But there is no such book for differentiation. Why? Because integration is, as I said, tedious, and they usually, students or even teachers find difficulty in carrying on the integration, for example, on the blackboard, so why don't they consult books? For example, here, these two functions, they look similar, and the derivative also are very much similar, yet the antiderivative of one is 10 minus 1x. Look at the antiderivative of the other one, yet both resemble a little bit each other, but yet they differ very much in their antiderivatives. So antiderivatives to find are not really an easy task. Again, the antiderivative of f is not unique, and this is one important thing. Usually we don't tell a student find the antiderivative of function. No, but we tell him find an antiderivative of function. Why? Because you may have different functions having the same derivative. For example, this one and this one and this one having the derivative of x cubed, and therefore all of them are suitable to be an antiderivative of the original function x cubed. Again here, this is a function that we've seen before, and this could be the derivative of mod x. Mod x, which is the absolute value of x, had the derivative 1 from the right-hand side and minus 1 from the left-hand side, and is not differentiable at x equal to 0. So you might find that derivative is some sort of function like this one here. But this, so whereas this function has an antiderivative of mod x, it can also have this antiderivative, because when you differentiate this function here, you get this one. You here again it is 1, and here it's minus 1. So you can take as antiderivative of this function this one. So as I said, there is no one simple antiderivative of a function, but you may have more than a representation of the same function. So now what about when you have two antiderivatives, for example, capital F and capital J of small f? You should add C here. In other words, this is a theorem, and it has a proof. When you have two antiderivatives of the same functions, then they differ by a constant C. And this constant C is important. It's not a luxury that you put C. Students usually, they neglect it. They just find an antiderivative. No, you have to add the number C. And why we can see this here? This is an example in which C is important. You have, for example, the integral of sine x cosine x. Now, the integral of sine x cosine x is equal to what? You can write it as half sine square x. Why? Because when you differentiate this, simply, you have 2 sine x cosine x divided by 2, so you get this function. But again, you can also represent sine cosine x in this form, because sine twice x is equal to twice sine x cosine x. So you can put it in the form first half sine 2x, and then you integrate it. But when you integrate this, you have minus 1 over 4 cosine 2x. But cosine 2x, there's a mistake here, is equal to 1 minus 2 sine square x. So whereas 1 minus 2 sine square x divided by minus 4, what you get? You get 1 over 2 sine squared, which is the same one, minus 1 over 4. So which of them is right, this one or this one? Actually, neither of them. This one should be added, a constant C1, for example, and this one C2, and then you have C2 minus 4 is equal to C1. In other words, in either of the two, you have to add an arbitrary constant. And this is why, for example, in application, suppose, for example, you are throwing a stone, for example, up the cliff with a speed, for example, v naught, and you wish to calculate the distance at which this stone reaches. What you do is that you apply, for example, the law of Newton, which is the second law of gravitation. Here, d2y by t squared is equal to minus g, and then you integrate it, so you get the velocity dy by t is equal to minus gt plus a constant. Here the constant is equal to v naught, because at t equals 0, the velocity is equal to t naught. So you see now with the integration, you have to add up c, because c here stands for something practical, something real, physical, which is the speed v naught. You may throw it at the speed of 10 meter per second or the speed of 30 meter per second. The problem is the same, except that the arbitrary constant means something physical. And so actually, when you add here, for example, 10, what you mean is that you have a family of curves. Each one is a function of t, which represent the velocity. This one is your problem, in which the speed of by which the speed you throw the stone, the initial velocity is 10, whereas you can find another curve in which, for example, the initial velocity is 30, etc. So you have here a family, and this is the meaning of the integral. Your integral or indefinite integral, the meaning of which is if you have a family of antiderivative. And when you integrate it further, you have y is equal to minus half g of t squared plus 10t plus c. Here again, when t is equal to 0, you can tell the value c, which is the height at which you throw your stone. It can be the surface of the ground, or it can be the vertex of a hill, of a cliff. So this c again gives you a family, another family of antiderivatives. Each one of them is a solution to the original problem. So the original problem is the same problem here, whereas it applies to different family of antiderivatives. Each one of them could be a solution to your problem, depending on the condition which you impose on your problem. And this is why we say that the idea or the meaning of the indefinite integral is that you have an antiderivative, but the family of all these antiderivatives constitute what is called the indefinite integral of your function. For example, here you have f of x is equal to cosine 2x. So what is the integral of cosine 2x? When you integrate this, you get what? You get half sine 2x, because when you differentiate, half sine 2x is equal to cosine 2x, but you have to add c. As I said, it's not luxury, you have to add c, because c represents what? What you have here, a family of parallel curves. Each of them is suitable to be a solution to your, in other words, it's a candidate. Each of them is suitable to be a candidate for your original problem. These are some antiderivatives of function. You have to have, usually students in books, in textbook, they list all these functions here because you're going to use them in the fundamental theorem. So what's the integral of x to the power n? It's x to the power n plus 1 divided by n plus 1. Of course, you have to add c in all of them. And here, when you differentiate this, you get x to the power n. Again, when you differentiate logarithm mod x, you get 1 over x, etc. So these are not important to stop here. All you have to do is just consult the books to know the type of antiderivatives of some elementary functions. Again, these are some properties of indefinite integrals. For example, the derivative of the integral is the function f of x. And this is, of course, simple by intuition. Something that you integrate and then you differentiate, you get f of x. And remind you, it is written like this, but it could always be written in the form of d by dx from a to x, f of t dt is equal to f of x. And this is actually the theorem of Cauchy. Like if f is an integrable, is a function having an antiderivative, then the integral, this is the fundamental theorem, the integral of d by dx, the integral of f of t dt from a to x is equal to the antiderivative of the function x. So when you differentiate it again, you get f of x, so, but we don't usually put the limits of integration, and we just, because all the time we have indefinite integrals, so we can be contented with an integral of this sort. So the derivative of an integral is equal to f of x. And of course, the contrary, of course, the converse situation also, you may have, for example, the integral of a differentiation. Like this one here, when you differentiate a function and then you integrate again, what you get? You get f of x, but you don't forget the constants. For instance, for example, here, this is the derivative. This you apply directly to this, to the first one here. The derivative of cosine square root of x squared plus 1 is equal to cosine x squared plus 1. Now, again, some properties of the indefinite integral. If f and j are two functions which have antiderivatives on an interval I, then it is natural that when you multiply the function by a constant, then you multiply the integral by the same constant. In other words, you don't have to, you multiply the function, you just carry on with the integral and then you multiply it with the constants. Again, the indefinite integral of the sum of two functions is equal to the sum of the indefinite integral of functions. So for example, if you wish to evaluate such, for example, indefinite integral, what you do is that here you apply the theorem. In other words, you sum up the integrals of each. So for example, the integral of the square root of t is 2 over 3, t to the power 3 over 2. The integral of sec square is tan, and the integral of 1 is t. So you get this formula expression here at the end. The integral of y plus 1 over y d square. These sort of integrals are very simple. What you do is that you expand the bracket. You have here, for example, you square y square plus 1 over y square plus 2 twice y times 1 over y, which gives 2. This is the simplest way of doing it, and probably it could be even the unique way. And then you integrate a term y by 1. The integral of y square is equal to 1/3 y cubed. The integral of y over y square is equal to minus 1 over y, whereas the integral of a constant is equal to y. So you have here c. you add up always. You don't ever forget about this constancy, because as I said, your indefinite integral is a family of solutions, and you have to pick up the particular solution suitable for your application. Prove that the double derivative. Here, what you do is that you apply directly the theorem that the integral of a derivative is equal to the function plus a constant. So all you have to do, if you wish to arrive to this result here, you can actually, this is the theorem we have just seen before. The integral of the derivative is equal, of a function is equal to the function plus c. So you can put u is equal to f prime, and you can, or f dash, and you can get this directly. So you apply your previous result. Here it asks you obtain, if you have a kind, this is a simple form of integral equations where you are given the integral and you wish to calculate the function. So what you do, you can differentiate both sides, because when you differentiate the left hand side you get f of t, and the right hand side, this is you apply here the chain rule. It's the minus square root, or you can say minus 9 minus t square all to the power minus half, and you can put 9 minus t square is equal to u. You differentiate with respect to u, so you get u over 3 over 2, and then this is the composite function between the integral of 1 over square root of u, and you differentiate what's inside u by dx, so you get minus 2t, and 2 cancels out, and this, and you get this solution here. Obtain f of x. This is a simple, what you call a simple differential equation. You have, for example, here d2y by dtx squared is equal to x minus 2, and you are given initial condition, because I told you before the solution of any form of derivatives, in other words, when you integrate, you have a family of solutions. You have to pick up one here, because it's a second order equation, so you have to have two initial conditions here. So what you do is that you integrate this, and you use this formula. Of course, it's not important whether c comes here or there. The integral, we've seen before that the integral of f double dash of x dx is equal to f of x plus c. Whether you can put minus c or c doesn't matter. So you start from here and you integrate x minus 2. When you integrate x minus 2 from here, you can add up also another constant, and you can add it up to c. It's not important, and this is why we call it c1. If you don't call it c1, you call it c, doesn't matter. It's an arbitrary constant. So you integrate this, you get half x squared minus 2x. And then here you end up with what? That f dash of x is equal to this expression, but you need to calculate c1. So you go back to the initial conditions. Here you have when x is equal to 0, f prime is equal to 2, so you put here 2 and 0, so you get c1 is equal to 2. And then you proceed further. Now you have here dy by dx is equal to this. What is the value of y? What is the value of f? Now you integrate this again, you get 1 over 6, because here is 1 over 3, 1 over 6 x cubed minus x squared. And then you integrate 2, which is 2x, and then you add up another arbitrary constant. But again, you consult the first initial condition here. When x is equal to 0, c is equal to what? F of x is equal to 1, so c is equal to 1. And therefore, and this is your final solution. This is one solution out of the many family of solutions that you have arrived at, including these initial or these arbitrary constants. This is another equation here. dy by dx is equal to y. And given y0, y of note equal to 5, show that y is equal to 5 to the power e to the power x. Now here, these kind of equations, they call them differential equations separable, but there is no need to integrate it. Dy by dy is equal to t of x. You can invert this. You can invert it this way. If you invert this equation by writing it in the form dx by dy is equal to 1 over y, what you get here is what? Is x as a function of y, and the derivative is equal to 1 over y. So you directly find an antiderivative of 1 over y, which is what? Which is the logarithm. So you have here dx by dy is equal to 1 over y dy, so x becomes what? The integral of this, which is ln y plus c. Now, what is the value of c? You go back to the initial condition. When x is 0, y is equal to what? To 5. So c is equal to what? 0 minus ln 5. So c is equal to minus ln 5. You substitute c here again, minus ln 5, and you get at the end what? X is equal to ln y minus ln 5. But ln y minus ln 5 is equal to ln y over 5. And from here on, the inverse function of this function is what? Is y over 5 is equal to e to the power x, or y is equal to 5 e to the power x. This is a simple differential equation. These are simple differential equations. We call differential equation when you have the algebraic equation, when you have an equation in a variable x, for example, and you wish to calculate the value of x. For a differential equation, you have an equation relating y with y dash, for example, with dy by dx, and you wish to solve this to obtain y. So we call this a differential equation. In other words, there is a solution to this, and this solution satisfies the differentiation formula in which you are given. So for example, this is a differential equation. Y dash is equal to xy cubed. In other words, you have dy by dx is equal to xy cubed. So what you do, you can isolate the variables. For example, here, look at this one. This is called a separable differential equations. And actually, you remember in our introductory lesson when we spoke about the calculus of Leibniz, I told you to use these notation because these are the easiest. And I always recommend the students to use the notation of Leibniz because you will be able to transform your calculus into real calculus. In other words, into algebraic operation. And this is exactly what you do here, using the notation of Leibniz. Dy by dx is equal to x squared y. So you can here divide both by y and you multiply by dx to obtain this equation. Now this is easy. Once you do this, you can integrate both parts, this with respect to x to obtain 1 over 3x cubed, and this with respect to y to obtain ln y. And here it is, you solve the equation, as I said. So you solve them. So what's the value of y now? Here you can let c be equal to the logarithm of another constant, for example, and you subtract it from ln mod y, so you get ln mod y minus ln another constant, and you can express them in this simple form. This is a nice problem that I borrowed from a book. And it says that it's an application at the same time on differential equations and applications on the indefinite integral and how indefinite integrals are, they are very suitable in finding in finding solution to practical problems. Here it tells you that a person was murdered at some time. The police doesn't know. But when the police arrived on the scene of the crime, at 10 o'clock in the morning, the temperature of the body was 20 degrees centigrade. And after 1 hour, the police were there inspecting the apartment. After 1 hour, the temperature dropped to 18 degrees centigrade. Now, if the room temperature is 10 degrees centigrade, the police asks himself, he tries to look for the time of the murder, the instant at which this person was murdered. Probably he must have consulted a mathematician or a physicist, I don't know, at that time of the crime, because I wasn't there then, but at least this is a very nice practical problem at which you can apply your the equations that we have just been the kind of differential equations, because this is a differential equation in which we seek a solution. And the solution, of course, there is not one solution. We have to pick our solution that is suitable to this particular problem. So what we do is that we have to find a model. This is called a model. The model that is governing this sort of equation. Well, the model is called Newton's law of cooling. Newton's law of cooling tells you that the derivative of the temperature with respect to time is either increasing or decreasing, doesn't matter. If K is negative, then it attenuates, it decays, temperature decays, because the solution of dt by dE is equal to K of T. You can, of course, isolate the variables. You can get here like this. Here, when you have dt, capital T, temperature by the time is equal to T, so you have dt by t is equal to dt. With the integral of both, this gives you what? This gives you a logarithm of t, and this gives you t. It means that capital T is equal to e to the t. So here, it means that the temperature, either it rises or it decays depending on the sign. So if this here, there is a sign here, you get here a sign negative. If it is positive, it's positive. So actually, this Newton, although it's called Newton's law of cooling, yet it applies also when the temperature rises. So anyway, what the police has done is that he used this formula here and he integrated it. So this is a differential equation, and you can separate the variable. How? You divide both by k or you divide by capital T minus 10 here to obtain k dt is equal to d temperature by temperature minus 10. And then you integrate both sides. When you integrate the left-hand side, you get what? You get the logarithm. This is the integral of 1 over t minus 10. Whereas from the right-hand side, you get k of t plus c. Now, this is the solution of your equation. Whether he has been murdered at 6 o'clock in the morning or 3 o'clock in the afternoon, it doesn't matter. This applies to all kind of bodies or of situation in which the body cools down or the temperature rises. It doesn't matter. And then here you have to apply, because as I said, the indefinite integral is the family, the solution of which is the family of antiderivatives. So this is the antiderivative, and you have to add up C, and then you consult your problem. The problem is what? At 10 o'clock in the morning, the temperature was 20 degrees. The police measured the temperature of the body. He found it to be 20 degrees when he arrived at the scene of the crime at 10 o'clock in the morning. And then when he stayed another hour at 11 o'clock in the morning, the temperature, the body cooled down to 18 degree temperature Celsius. So now you have two here, you have two initial conditions. You can apply to this equation. In other words, when t is 20, t here, small t is 10, and when t is 18, small t is 11. So what you do is that you have two equations in two unknowns, which you can solve them, as a matter of fact. You can solve them to obtain what? You have two equations in two unknowns. The two unknowns are k and c. You don't know them. So you can subtract them and get k. And here it is, k is negative. Why is it negative? Because either you can assume that it was cooling down, so you put k a negative value, or you can leave it as it is, because this is a general rule or a general law which applies to all situations in which the temperature changes, whether it cools down or the temperature rises. And here you find it negative because, in other words, the body was cooling down in temperature, and then you find C as well. So now you know both K and C. Now you want to know the time at which the temperature reaches either 20 or 18, at which particular, what you do, you know very well that at the instant of the crime, the temperature of the body is 37, because he was living. So since you know from the equation that the temperature is 37, now you can go to the equation, back to the equation, you know C and you know K, so all you have to do is that you substitute for your temperature to be 37 degrees, and you get T, and T becomes equal, you solve it to obtain T, and T is equal to 5.5 a.m. It means that although you arrived to the scene of the crime at 10 o'clock in the morning, you discovered that the crime has been occurred at 5:30 a.m. So this actually is a nice application to see how differential equations manage problems in which you have variations and which you have rates of change, and from the rate of change you obtain the solution of such equations. Now, with this, we have come up to the end of our lecture. Yet there was a slide I wish to show it to you. This one here. This, because you remember at the beginning of the lesson, I told you that there was a question, a chronic question that was brought about during the whole evolution of calculus, whether antiderivatives are integrals or not. And I said that Cauchy resolved this issue, that antiderivatives are integral, but they are indefinite integrals, and Newton as well in his first fundamental theorem. And he just shows you that you have, for example, here half a circle, and the equation of which is f of t square root of 1 minus t squared. Now, if you integrated between a and x, you get a solution capital A of x, and capital A of x here represents what? Represent the antiderivative of this f of t. Here it is. This is the antiderivative, and at the same time, this is an area. Why it's an area? Because you can check. You can rightly put x equal to 0. You get area equal to 0. If you put x is equal to 0, here what you get pi by 4, and this is exactly equal to 1/4 of the circle. Whereas when you put x is equal to 1, this cancels out, and this gives you pi by 4, so you get pi by 2, and of course this gives you the half the circle. So it means here actually, when you integrate this function here, you get another function, capital A of x, which is at the same time, it's an area, and at the same time, here look at this line here, this is the antiderivative of the original function. So antiderivatives are really integrals, but they're indefinite in the sense that they don't give you a number, but they give you a function, and this function represents an area under a particular curve at a particular value of x. And with this, we come to the end of our lecture. of antiderivatives or of the indefinite integral, and we move to another lesson next time. And until we meet, I wish just to remind you, like every time I do, that all these lectures are uploaded to the site of the Unituno Telematic University. And until we meet again, thank you for your attention and very good luck.